Hi everyone, we're going to learn about titration in this video, which is an important lab technique. It's basic to any introductory chemistry curriculum. So how does it work? And what is the objective? Well, titration's objective is to determine concentration of a solution. So while we might refer to an unknown, what's unknown is simply the molarity. We know the identity of the solution. In this case, I'm going to do a titration of aspirin, which is an acid, and I'm going to use a base to titrate it. There are many different types of titration, but in this course we're going to focus on acid-base titration, and we'll keep our discussion limited to strong acid, strong base titrations. Now, an acid-base titration involves an acid-base neutralization reaction. You can add acid to base, or in this case, add base to acid. Now we're neutralizing one chemical with another, and we're going to use a pH meter or an acid-base indicator, like this substance called phenolphthalein, which is going to turn pink when the solution becomes basic. Either way, we'll be able to determine the endpoint of the solution, or the endpoint of the titration. What's the endpoint of the titration? At the endpoint, the solution has been neutralized. For a strong acid, strong base titration, the solution will be neutral at the endpoint, and the hydronium ion concentration and hydroxide ion concentration will be equal. That means the number of moles of acid is going to be equal to the number of moles of base at the endpoint. And that will allow me to determine how many moles of acid there may have been present in the solution to begin with, or there must have been present in the solution to begin with. I'm going to keep adding base until I've neutralized the acid. If I know how many moles of base were used to neutralize the acid, then I know how many moles of acid must have been present. And we can calculate the number of moles of base used because we know the molarity of the base and we know the volume of the base that was used to reach the endpoint. Remember the formula N equals mV. The number of moles can be calculated if molarity and volume are known. Now, the number of moles of base can be calculated since we know molarity and volume of the base. And we can calculate the molarity of the acid as a result, knowing that these two number of moles are equal. The formula becomes MAVA equals MBVB. This can be used anytime we're talking about a monoprotic acid, in other words, an acid which only has one ionizable hydrogen, and a monobasic base, one that only has one hydroxide ion per mole, like sodium hydroxide. We're going to limit our discussion to this kind of a scenario, and we're also only going to examine strong acid, strong base neutralizations. That makes this formula applicable to all the scenarios we're going to use. MAVA equals MBVB might look a little bit like MIVI equals MFVF, but please know, while they're similar mathematically, they pertain to very different scenarios. MIVI equals MFVF is about dilution, and this equation is about acid-base titration and is only valid at the endpoint when neutralization has occurred. So let me show you what the procedure actually looks like. So in this procedure, I'm going to be neutralizing an acid with a base. The base is in the burette. I know the concentration of the base is 0.1 molar sodium hydroxide. That is called the titrant. The titrant is the substance with known concentration that we use to neutralize the analyte. The analyte is the substance with unknown concentration, which we're trying to determine the molarity of. We're going to slowly add titrant to analyte and see how much is required, how much base is required to neutralize this acid. Now, I've rinsed the burette with the titrant to make sure that the concentration in the burette is known, and I'm going to add just a little bit at a time. But I'll need to determine how the pH of the solution is changing, and I can do that two ways. I can measure the pH with a pH meter, or I can use an acid-base indicator. In this case, I'll use an acid-base indicator. The acid-base indicator we're using is called phenolphthalein, and phenolphthalein is a pretty difficult word to spell. However, it's a pretty commonly used acid-base indicator. It will turn pink in basic solution. We only need to add a little bit to our solution, and if it's basic, it'll turn a bright pink. Now you can see it's colorless right now, and that's because this analyte is acidic. What we're analyzing here is an aspirin tablet, which I've dissolved in water. Now I'm going to start adding base, the titrant, and I'll add just 1 milliliter at a time. Now you may see that a little bit of color appeared for just a moment as I added that 1 mil. That's because momentarily there's an excess of hydroxide ions that have yet to react with hydronium in the acid solution, but it doesn't take long. As I continue to add base, we'll see that pink color stays a little bit longer each time. There's the second mil and the third mil. Now, I'm estimating, and reading a burette can be done with a great deal of precision. So in a more careful lab technique, I would want to record the volume of base each time. In this case, I know where my endpoint is approximately, so I'm going to jump to the point where the solution is starting to retain that pink color for a little bit longer. I'm getting closer to the endpoint because when I add a milliliter of base now, the pink color stays for a little bit longer. See if you can see the pink color that I'm talking about. That definitely stayed for a little bit longer. I'm going to slow down, and instead of adding 1 mil at a time, I'm going to add 1/10 of a mil at a time. Now at that point, that pink color stayed for quite a few seconds and has very gradually faded to clear. I know I'm very close to the endpoint now. If I add just another 1/10 of a mil, that pink color should stay. Now you can see you've got a very bright dark pink solution. I may have even over titrated by 1/10 of a mil, but it didn't take very much to push it over the edge. So what was the volume reading on the burette when I reached the endpoint? The volume of base that I added to neutralize the acid was 18 mils. I can record that to the nearest 1/100th of a mil. Only tenths are marked on the burette, but we can always estimate 1 digit beyond what's marked. So that's a fairly high number of significant figures. If I used 18 mils to neutralize the acid, I can figure out the concentration of the acid using this equation. MAVA equals MBVB. I know the volume of the base that was used, and I know the molarity of the base. The molarity of the base that was inside the burette was 0.2 molar. I knew that to 3 significant figures. I want to solve for the molarity of the acid. I also need to know how much acid was in the flask when I began titrating. I had a 150 milliliter sample. Now notice that I've had both these volumes in milliliters. They could both be in liters, but they do need to be compatible units before we can plug this into equation. Let's solve for the molarity of the acid. The molarity of the acid can be given as MBVB over VA. Let's go ahead and plug those numbers in. MBVB would be 0.2 molar multiplied by 18 mils, and VA is 150 mils. So the molarity of the acid is 0.024 molar. I can report this answer to 3 significant figures. Notice the least number of significant figures here is the molarity of the titrant. So that's going to limit how many digits I can include in my answer. Let's try another problem. See if you can identify which variable is which in this question. Pause the video for a minute and see if you can identify what the question is asking for. I'll go ahead and populate the list here. We're going to use MAVA equals MBVB. The unknown we're solving for here is the molarity of the acid, and the volume of the acid is given as 15 mils. Did you identify the molarity of the base and the volume of the base? They are 0.125 molar, and the volume of the base, 7.5 milliliters. Now notice I've kept both volumes in milliliters. You could have converted both of those to liters. Now we'll go ahead and rearrange MAVA equals MBVB to solve for MA. We'll do the calculation, and we get 0.0625 molar. That should make sense if we consider the fact that the volume of the base needed to neutralize this acid was only half the volume of the acid that I began with. So the base must be twice as concentrated as the acid. And it looks like if this was only given to two significant figures, really, I should round my answer to two significant figures as well. Let's try one more. Try pausing the video here and seeing if you can complete the problem. Start by filling out the shopping list. The volume of the base is 18.7 mils, and the molarity of the base is 1. The molarity of the acid needs to be solved for, and the volume of the acid is 5. Assuming we're limited to two significant figures, we get 3.7 molar. Now, not all problems are going to be solving for molarity of an acid. Sometimes you might solve for molarity of the base, or you might solve for the volume of base needed if the molarity of the acid is known, and so on. Let's look at one other type of problem. This one's a little bit different. See if you can pause the video and solve it. Did you correctly identify that this problem is asking for volume of acid? The molarity of the acid is given as 0.275 molar, and it asks how much of that would be needed to neutralize a basic solution. The base is 0.15 molar, and the volume of the base we're trying to neutralize is 25 mils. So this time we want to rearrange the equation to solve for VA. The volume of acid that would be needed is 13.6 mils. If we only know the molarity of the base to two significant figures, we can only really estimate that answer to two significant figures. About 14 mils of acid will be needed. So we've looked at titration, how the lab procedure works and how the calculations work. Notice that we can titrate acid with base or base with acid. In the example we gave before, I was adding base to acid, and so the analyte was clear until I reached the endpoint, at which point it turned pink. Conversely, if you're adding acid to base, you may start, if you're using the same indicator, with a pink basic solution that will become clear at the endpoint as the hydroxide is neutralized by the acid titrant. Finally, keep in mind that this is only one example. There's many different types of acid-base indicators. Phenolphthalein is commonly used because it turns pink at a pH of about 8, so just past the endpoint of a strong acid, strong base titration. And there are other indicators which are used in other circumstances. We're limiting our discussion to strong acids and strong bases, and where weak acids and weak bases are involved, we have a little bit more of a complicated situation to analyze. In the next video, I'm going to show you a simple titration lab and ask if you can answer a few questions about it as part of the lab activity for this week. We'll see you next time.